So first of all, I should say that almost everything in the first half of this talk is in standard textbooks in quantum field theory. I will explain how to assign integrals to graphs. And in the second half, I'll give a sort of informal survey of what is known and what is not known about these integrals. And the problem in this subject is knowing where to start. So typically a quantum field theory course will talk about the Feynman path integral up to a certain point, and then by analogy they'll make some noises about Wick expansion in graphs, and then sort of start again perturbatively, and there's a sort of leap of faith that connects the two parts. So what I will do is start the story then with perturbation theory. That seems as good a place as any. So as I just said, we want to put graphs at the center of the story. So in perturbative quantum field theory, interactions between graphs are represented. Sorry, not a good start. Interactions. Interactions. It's early in the morning. Interactions between particles are represented by graphs. I always feel slightly awkward as a mathematician talking about these things. Here's an example of a graph representing two particles scattering and exchanging a photon. Here's, for example, another graph. The same two particles exchange a photon, which spontaneously becomes an electron-positron pair, and which later annihilate to form a photon again. So every graph that we'll draw like this represents some kind of interaction between fundamental particles. And the game is that to every such graph, physicists associate an amplitude Ig, which is given by some integral, and it's going to be a function of certain data, which are masses and momenta of particles. So it's a function. And the final answer that you compare with the experiment are obtained by summing over all graphs. And of course there are infinitely many diagrams of this type which represent the same outcome, the same observed outcome. And so one has to do something. You can only in practice sum over finitely many graphs. And so at this point you cross your fingers and hope that somehow this expansion converges, which it doesn't. So I'm not going to say anything about this. There's some very difficult unsolved problems relating to this, but we run into some divergent series, and we don't worry too much about that. Practice it. This all seems to work. Okay, so today, to make some simplifications, I'll work in a scalar field theory, and I'm going to work in Euclidean as opposed to Minkowski spacetime. So spacetime will be r to the d, where the dimension is a positive even integer. So it's important that it's even. And so we'll work with a Euclidean norm So x squared is the sum of the square of its components. So if x equals... Okay, and so the challenge that I want to bear in mind throughout this talk is how we think about amplitudes. So how do we make sense of the zoo of amplitudes Ig. So this won't make much sense now, but when we've seen some examples, I want you to think about the problem is, the challenge is to try and find some order in this huge morass of examples. So of course I should say that calculating these Feynman amplitudes is big business. Nearly all the predictions for particle collider experiments are obtained by calculating amplitudes Ig and comparing them with experiment. So there are, I don't know how many people, but many teams around the world, banks of supercomputers running night and day calculating amplitudes. This is, and if you open any particle physics phenomenology paper, journal, it will be filled with huge expressions for Feynman amplitudes. So this is a very important problem, and we are very far from having a mathematical theory of amplitudes. Okay, so let's actually begin. A Feynman graph for me then will be a graph. So a graph has a certain set of vertices, certain set of internal edges, and a set of external edges. Okay, so this is a graph, so it satisfies the usual rules. And the internal edges, each edge is connected to two vertices. So this is just a subset of pairs of vertices. The external edges, on the other hand, are connected to a single vertex. We represent that by a map from the external edges to the vertex to which they are attached. So here's an example of a Feynman graph. Just a triangle. Has three vertices, three internal edges, and three external edges. For convenience, I'll number the edges for later use, 1, 2, 3. And the external edges represent particles which I will typically represent as incoming, but not always, in fact. Okay, so Feynman graph also has some extra data, namely the data of...
Il y a seulement au plus une arête pour, entre deux points donnés.
Non, il peut y en avoir plusieurs.
Donc c'est pas une inclusion.
Oui. Merci.
Il peut y avoir des boucles, bien entendu.
Voilà. Une implication.
Oui. Merci.
Et le graphe est orienté toujours.
Non, pas encore. So the graph is not necessarily oriented. No. But I'm going to orient it in just a minute to write down the integral, the Feynman integral, but it won't depend on the orientation. So the graph also has an extra data of a mass, a particle mass, me, which is a real number. If you're paranoid, you can take it to be positive, But as we'll see, it's only the squares of the masses that come into the formulae. So there's a mass for every internal edge. And to every external edge, we have a momentum Qi, which is a d vector, for every external edge. So here, let's put Q2 here, Q1, and Q3. So the convention will be almost always, sometimes I might change this, the convention will always be to have momenta coming inwards. If you reverse the sign, if you want to represent an outgoing particle, that's the same as an ingoing particle with the negative momentum. So we can always assume that all the particles are incoming if we allow the QIs to be negative. So that's totally fine. They're vectors, yeah. So that's a very small detail. And the next remark is that this data is subject to momentum conservation. Momentum conservation, sum Qi equals 0 for all external edges. Okay. Right, so now we want to write down an integral associated to such a Feynman graph. So Feynman graph is the graph with this data. And to do that, we need some integration variables. So to every edge E, internal edge, to every internal edge, we assign a momentum variable Ke, which is a d vector. Now, sort of temporarily, I'm going to choose an orientation on the graph, just to write down the integral, but it won't depend on this. The integral won't depend on this orientation. So choose an orientation. You'll see why in a minute. And let me write PE to be either KE if E is an internal edge, and the incoming momentum if E is external edge. And then the Feynman integral in momentum space form is so this depends on the external momenta Qi and the particle masses me. So it's an integral over real space of d dimensions, product over internal edges, d-fold integral. So remember, Ke is a d vector, so integrate. This is the component by component. And here in the denominator we have Ke squared plus me squared times the product over all vertices, and here a delta function PE, where the sum is over all edges, both internal and external, which meet the vertex V. So this makes sense because we've chosen the orientation. The meaning of this
does it make sense? Integration not over RD to power second.
Oh, thank you very much. RD to
Number of edges.
times E.
Internal edges.
Yeah, let me give that a name now, actually. Ng, thank you, equals the number of E int G. Yeah, thank you. So this is RD times NG. So this factor here is represents, if you like, momentum conservation at every vertex. So that the sum of the momenta at every vertex sums to 0. Okay, so this, of course, is the momentum space Feynman integral, as it's most commonly seen. Of course, it doesn't necessarily make sense. It may diverge. Sorry? A small d. Oh, this is delta function. D?
It's limit measure.
In D dimension.
Oh, here, d. Oh, sorry, d as in, yeah.
And the delta is?
Delta is the Dirac delta function. Okay, so mathematicians tend to prefer a.
Sorry?
Yeah.
You're assuming that at each vertex, your convention is such that all momenta are either in.
No, I'm going to choose. Well, you could do that. But I'll show you in an example just a minute. But I said we choose an orientation on G, and then when we assign a momentum to every edge, so we'll have. Oh, let's do it. We'll have K1, K2, and K3. And so at this vertex, we'll get the equation K2 plus K3 equals Q1. And then at this vertex, we'll get K1 plus Q3 equals K2. And at this vertex, we'll get K1 plus K3 equals Q2. So that this delta function means integrate over this region.
Okay. So it's sum of plus minus. Because if you choose orientation.
It's clear what it means.
If you change the orientation, you change one key into the opposite, and it doesn't change anything.
Yeah, sure. Yeah, no, but strictly speaking.
This integral doesn't make. I have to say this integral doesn't make a huge amount of sense in the first place, and that's why the first thing I'm going to do is change it into an integral which does make sense. So this is what you see in physics textbooks. I've kept it exactly as it's written, and exactly as I'm going to say is that in fact in the good old days, it was common practice to use parametric representations. That's classical, and in fact it's after a long hiatus, it's now coming back into fashion. So classical and modern approaches use the parametric form, the parametric representation, which is much more satisfactory from many points of view. So I'm now going to derive that from this, and all should start to make sense. Yeah?
Do you need to introduce coupling constant for each vertex?
Do I need to introduce what?
Coupling constant.
Yeah, but I'm working in principle, yes. Absolutely. But I'm working in a very simplified, this is a simplified a theory where I can just take it to be 1 or something. I could put a parameter. You can, yeah. But I'm only going to consider one graph at a time, so we know how many vertices it has. Doesn't make much difference, yeah. Of course, in a genuine quantum field theory, the true Feynman rules are much, much more complicated. But at the end, I'll say something very briefly about how that changes.
Just to make IG the sum over the IG as a formal power series sum.
Yeah, I think of it as a formal power series, exactly. Yeah. Okay, so to get from this to parametric form, we'll first apply the Schwinger trick. So this is the identity 1 over x equals integral of e to the minus alpha x dx, d alpha. So this is valid for x positive. So the idea is to introduce a new variable alpha e for every edge, every internal edge, and then write, and in this integral, replace this factor here with integral from 0 to infinity e to the minus okay, so this is something, it looks as if we're going in the wrong direction. Instead of doing the integrals, we're adding more integrals. But as we'll see, there's a lot to be gained from this. So what happens to this integral? It becomes, it will now be the integral, well, a bunch of integrals from 0 to infinity for every alpha parameter assigned to every edge, r to the d and g, exp minus sum e k squared plus me squared alpha e, and then the same stuff so that's the same as before, I won't write it out again, and product d alpha e. Right. So we made the integral more complicated, apparently, by introducing new variables. But now the point is that we can actually do the momentum integrals now. So this involves Gauss's formula for this integral over the reals, e to the minus pi x squared dx equals 1. So you can multiply integrals of this form together, and to get a higher dimensional version, and that in general the d-dimensional analog of Gauss's integral is as follows. If we have q of x is minus x transpose ax plus 2b, where, so here x is an RD, A is a symmetric positive definite matrix, and B is any vector in R to the D. So this is a nice quadratic form. Then the integral over R to the D e to the qx dx. Oh, sorry, thank you very much. B scalar x. Let me put B transpose. Yeah, thank you. Sorry. Of course, if we add a constant this will come up later. If we add a constant plus c here, it's just going to factor straight out of the integral because it does not depend on x. Okay. Yeah, thank you for that. So the upshot is that this is pi to the d over 2 over the square root of the determinant of A times e to the b transpose A inverse b. Right, so, and this can easily be deduced from the previous integral by diagonalizing the matrix A. And it'll break into a product of d copies of this integral up to a change of variables. Right, so now the idea is to apply this identity to the integral at the top and to actually do the KE integrals in this expression in the above. And the upshot will be that we will obtain a new integral only in, there'll no longer be any KE's, there'll only be the alpha E's, the masses, and the QI. Well, only the alphas, the M's, and the Q's. Yeah. Okay, so this can be done in general, but it's quite tedious. So I will just illustrate on one example and then state the general answer. Okay, so let's do a very simple example. So let's take this graph. We assign momenta k1 and k2 to these two internal edges. So if you prefer, we can, if I should stick to my conventions, minus q. So the delta function in the integral is momentum conservation at each vertex. That reduces, they're both the same condition, so it reduces to the equation k1 plus k2 equals q. So if you like, that's our domain of integration. So now I'm going to write down the exponent. So the exponent in that integral, so it was minus k squared e plus me squared alpha e. So what is it in this case? It is alpha 1 k1 squared plus m1 squared plus alpha 2 . Okay, so the first thing to do is to substitute in the momentum conservation condition. So this is alpha 1 k1 squared plus alpha 2 q minus k1 squared. This term and this term. And then the mass terms are going to accumulate here. So then the first thing you have to do is to take this part and complete the square. Of course, you can always do this. In this case, it gives the the main coefficient is alpha 1 plus alpha 2, and then times k1 minus q alpha 2 squared. And now you need to add q squared. Sorry, this is plus. Let me get rid of the minus. That's better. Plus over alpha 1 plus alpha 2. Okay, so we've completed the square. So let's write this. So the next thing is to change variables. Well, the shift variables. I can call this k. So let's put k equals k1 minus q alpha 2 over alpha 1 plus alpha 2. And then this is just alpha 1 plus alpha 2 k squared plus the rest. And changing variable, of course, we're integrating over r to the d, so the integral is translation invariant, and from this representation we can then plug in Gauss's formula and write down the answer. So what we get is so this is just the term in the exponential. We have exponential of minus this integrated over k. All the stuff on the right just does not depend on k at all. It's just going to factor out of the integral. And we just have to integrate e to the minus alpha 1 plus alpha 2 k squared. And that's easy using this formula. So I'll just write down the answer. We get pi to the d over 2 integral from 0 to infinity d alpha 1 d alpha 2. The alpha 1 plus alpha 2 comes downstairs. And then all this stuff over here is unchanged. It factored out of the integral in the first place. Okay. So in the general case, so you can, this works in general. You can complete the square and put in the integrals. It's a bit of bookkeeping to work out what the answer is. At the end you get here you get the determinant of a certain matrix. And then you have to apply something called the matrix tree theorem to express that determinant in terms of some graph-theoretic quantities. But that's rather straightforward, and the final answer is that we get that the integral is some trivial factors, which I'm going to ignore, some powers of pi and so on, times the integral from 0 to infinity so here the product is over all internal edges. Then here you get a certain polynomial called psi g, and then you get exponential minus phi g q over psi g minus the sum So that is the parametric form of the Feynman integral. So I now need to explain to you what these psi and phi are. So psi g and phi gq are what are called Symanzik polynomials. Okay. Graph polynomials. So first of all, psi g. So psi g is a polynomial first discovered by Kirchhoff, I think in 1853. So it's a polynomial in just the alpha parameters and depends in no way on the external momenta or the masses. No dependence on Qi. It's an important fact that it has integer coefficients, but that won't play any role in what I say today. So here's a formula for it. Actually, there are many different ways to interpret this graph polynomial. I'll just give one. It is the sum over spanning trees in the graph, and then you take the product over the edge variables not in each spanning tree. So T, I should say spanning tree. So T is a spanning tree, means T is connected, simply connected. So that's means that it's a tree, and spanning means that it meets every vertex of the graph G. Or perhaps I should actually say, my apologies. Here G is, I'm assuming G is connected. Throughout this, I'm assuming G is connected. I forgot to say that. Otherwise, this is going to vanish. So let's do an example. Actually, probably the best would probably to do the example I did earlier. So let's do this example. 1, 2. It's very simple. There are only two spanning trees. There's one, it's a tree which meets every vertex, and there's two. And so the graph polynomial is the product of all the edges not in each spanning tree. So there's only one in this case, and it gives alpha 2 plus alpha 1. And alpha 2 plus alpha 1 is indeed the term that we found in the denominator here.
You should say that tree doesn't contain an external edge.
Yes, absolutely right. So I put no dependence on the QIs. Yeah, spanning tree. So think of T as a subset of the internal edges. Yeah, so the external external legs play no role in this at all. We just ignore them. Perhaps I should do another example. So this graph, which we had earlier, the spanning trees are 1, 3. It's going to be linear again. That's not a good example. I don't know, let's do this example for later on. So what are the spanning trees here? It's the same 1, 2, and 3. And so psi g is alpha 2, alpha 3, plus alpha 1, plus alpha 1, alpha 2. Okay. So that's one of the terms in the integral. And then we want the second semantic polynomial. Phi g. Now it does depend on the external momenta that I represent just by the letter q. So it's a polynomial, again, with integer coefficients in the alphas. And in fact, in dot products, scalar products of all the external momenta. So the formula is that's minus the sum over spanning 2 trees. And so now you take q to the t1. So the dot product is the Euclidean dot product. And then here you have the product of the edges not in T alpha E. So what is a spanning 2 tree? So T spanning 2 tree if and only if. So it's a forest with 2 components. So T has exactly 2 components, T1 and T2. It's simply connected. Each component is simply connected. And it spans. So spans means that it meets every vertex of the graph. Oh yeah, and then so what is q to the t1, q to the t2? So q to the ti equals total, the sum of all momenta entering the tree ti, total momentum entering ti. Okay. So an example. So let's do the example we did earlier. So spanning 2 trees, well, there's only one. It's this. It's the only spanning 2 tree, T1 and T2. And so we get minus Q dot minus Q times the product of all the absent edges. That's alpha 1, alpha 2. And that is exactly Q squared alpha 1, alpha 2, which was exactly, hopefully, the term up there, minus alpha 1, alpha 2 q squared. It's exactly the same polynomial here.
No, I didn't get this minus sign.
Sorry?
I did something wrong with minus sign.
Here or here?
No, because the polynomial is skewed a bit.
Yeah, no, but I put a minus sign here. Maybe you didn't see it here. There's a minus sign here. Yeah. Yeah, so the 2 minuses cancel to give a plus. Okay, let's do a more interesting example. The triangle graph we had earlier.
Ici, c'est moins le 3.
Là, non, là c'est bon, je pense. I think it's fine. No, I think it's fine. This is the definition of phi. But this is minus phi. So here, so this is minus phi, so it's minus alpha 1, alpha 2 q squared from that blackboard over psi, which is alpha 1 plus alpha 2. It's exactly this term.
But here there is no minus.
2 times
2 times minus is plus, yeah. So I think it's correct. So there's a minus here, don't forget. So often I don't put this in the formula, I write it differently. There's a minus here, and I think it all works. And there's a minus here, and then there's another minus here. 3 minuses.
If there is a minus here and there.
No, so with this dot product always produces a minus. So this, so minus.
because q to the power q2's notation is minus q to the power t1.
Yeah, thank you. Yeah, I was just about to say that. So qt1 plus qt2 is 0 by momentum conservation. So the way I normally write this is plus qt1 squared, and that equals plus qt2 squared. But if you write it this way, it's not clear it's symmetric in T1 and T2. But if you write it this way, it's obviously symmetric. But the price you pay is that you need a minus sign. But it's not. This minus sign isn't there. This is completely this has entirely positive coefficients. So this minus gets absorbed in this dot product.
So your 2 trees are disjoint.
Absolutely, yeah. Well, otherwise T would have a single connected component. It would be connected. One, I can't remember how I labeled this, but up to rotation, it's this. So what are the spanning 2 trees? Here they are. So here, let me label them. Q1, this is edge 1. Q3, Q2. That's one spanning tree. Q2, 2, Q3, Q1. And then the last one, Q3. Okay, so then, so what do? We take the dot product of the momenta entering the first tree, so it's minus Q1 dot Q2 plus Q3, and we take the product of the edges which are not present, so that's alpha 2, alpha 3. Same here. Minus Q2 dot Q1 plus Q3, alpha 1, alpha 3, and then the last one gives minus Q3 dot Q1 plus Q2, alpha 1, alpha 2. And then, of course, by momentum conservation, which I'll write up here, Q1 plus Q2 plus Q3 is 0. So this is just equal to Q1 squared, alpha 2, alpha 3, Q2 squared, alpha 1, alpha 3, plus Q3 squared, alpha 1, alpha 2. And of course, in the final answer, all the coefficients are positive. That's actually very important. And that's because we're working in Euclidean space. And that's what guarantees that these integrals make sense somewhere for at least some values of Q and M. And so these changes of variable formulae and so on will be justified in some region of Q and M and for some value of D. Not necessarily, which may be a real number, as I'll explain in a minute. So that's very important that these polynomials should have all positive coefficients. Okay, so, let me write. So this is not a standard notation, but I like to package this, give it a symbol. and consider this polynomial phi gq plus some me squared alpha e. So that's not a standard notation. And now, oh, yeah, thank you very much. Yeah, thank you. Thank you very much. Yeah, absolutely. So psi g is homogeneous of degree hg. So let me write hg is what physicists call the number of loops of the graph. So it's the dimension of h1 of the graph. And on the other hand, so phi gq and hence psi gq comma m are both homogeneous. Of course, in the alphas, they depend on other things as well, but of degree exactly one more, hg plus 1. So that follows from some combinatorial property of spanning trees. It's very easy to check. Okay. Right, so now we want to get to projective integrals. We want to get, actually, so there are two things you can do at this stage. We have these Feynman integrals in these form as an exponential integral. You can either do what's called a minimal subtraction, which I somehow prefer, but you can also do dimensional regularization. And I'm going to, the latter is slightly quicker and gets us straight to the answer, so I'm going to do that. And so what the basic idea is that we want to get rid of this exponential factor. So there's one that can be done by doing one more integration. So recall that we had I, the integral from 0 to infinity So let me rewrite it in the new notation. Exp over psi g. And now change variables. So write alpha e equals lambda beta e, where the sum of the beta e's equal to 1. Lambda is a positive real number. And then this differential form here, product d alpha e, can be written lambda. Recall that ng is the number of internal edges. D lambda wedge omega g, where omega g equals sum minus 1 to the I Okay, so that's a simple manipulation. And so this can be rewritten in the form where, in the region where the beta is all positive, and of course don't forget that the sum is equal to 1 of omega g over psi g. So now I view psi g as a function of the betas. It's homogeneous. So, but I'm not going to write beta e in here because it will clutter the integral. So this clearly means it's viewed as a function of the betas instead of the alphas. And here we get e to the minus lambda so from here over here, because of the degree of the psi polynomial is exactly one more than the degree of psi, when you scale all the alpha parameters by lambda, it will produce exactly one lambda coming out, because the degree here is exactly one more than the degree there. And we get lambda to the minus to the ng minus d over 2 hg d lambda over lambda. So this integral here we can do, and it's the final step, the final integral that we need to do. And it produces a gamma value, gamma of what I'm going to call SDG times psi g over psi g qm to the minus SDG, where so SDG is essentially this quantity which pops out, which is minus the number of edges plus d over 2 times the number of loops. And this is called, this is going to measure something about the convergence of this integral, and so it is called the superficial degree of divergence of the graph. It can be positive or negative. So essentially when it's positive, this integral is going to diverge, and when it's negative, it's going to converge. And it's called, the graph is called overall logarithmic divergent when it equals 0. Yeah, so everything's a function of beta. But I don't want to write beta everywhere because it will become very cluttered. But from now on, let me write the next integral, and everything is a function of beta. So the conclusion of all this is that we can write our Feynman integral up to maybe some trivial factors in the form, so it's going to acquire a gamma function then integral over this hyperplane. But in fact, you notice that the integrand that comes out is actually homogeneous of degree 0. So it's slightly nicer to write this as an integral over projective space.
Is the sign okay in the argument of gamma? Or you want the opposite sign?
Yeah.
You want the superficial degree of divergence?
No, I think this is correct. So superficial degree of divergence. So this is very positive when the graph is divergent. So this should be negative. Yes, it is.
But it's not what you wrote above. Because you wrote gamma of SDG.
Oh, sorry. Yeah. Thank you. Yeah, this is correct, and that is not correct. Yeah. Okay. Thank you. Yeah. So it measures how much it diverges. When it's very big, it means we're going to get a pole here. That's the point. So we get psi g d over 2 psi g over psi g qm to the power of. So I didn't put superficial degree of divergence here because I want to stare at it in a minute. So this is a projective integral.
It's not all projective space or simplex.
Oh yeah, sorry, thank you. Sigma. So sigma equals the set beta 1 Thank you. So this is a projective integral, and it makes sense if you plug in these degrees here. The integrand is homogeneous of degree 0. Okay. Okay. So now the problem is, of course, that this can have a pole. So this gamma factor can have a pole, particularly when the superficial degree of divergence is non-negative. So very briefly, the idea of dimensional regularization so the idea is that you replace and this is what is done the most commonly in practice, though I'm not a huge fan myself, is to replace d with d minus epsilon, some small positive epsilon, and perform a Taylor expansion in epsilon. And so what physicists do in practice is they compute the coefficients of epsilon to the I, where I can be both positive and negative.
Excuse me, why do you call this a projective integral? Okay, it's a question from a physicist, so I don't know this vocabulary. Could you explain more?
Yeah. Okay. So so you can view it as an integral over this hyperplane if you prefer, but the point is that you could have chosen any other hyperplane. We didn't have to choose wherever it is. The sum of the beta i's equals 1. You could choose any other hyperplane. It still works. And this, if you like, is a nice way to codify that. So what does a projective integral mean? It means that you restrict to an affine chart and calculate the integral on that affine piece. And that's exactly the same as choosing a hyperplane at infinity and integrating over affine real space. So for physicists, this is a way to think of this integral over r to the ng with a delta function given by this equation. And it contains the fact that you can replace this with any hyperplane, any non-trivial hyperplane. Yeah. Okay, so that's the end of the first half. As I said, almost everything is in textbooks. So I was informed that instead of having a pause, I should just press on. And so now in the second half, I want to give a sort of panorama of what we know about these integrals.
In this way, dimensional regularization doesn't need to invent a fancy geometry in 3.
No, absolutely not. No, absolutely not. No, absolutely not. That's the point. That's the key point. Okay. So a panorama. Okay, so what do we know about Feynman integrals? Of course, it's impossible for me to give a completely exhaustive list, but let me try to give a picture of the landscape. So the first remark is that the general one loop diagram. Oh, sorry. Let me make a remark. Before I do this, So this procedure, the Schwinger trick and Gaussian integrals and all this, works for in much greater generality. It works for gauge theory. And the upshot is that we can always write Feynman integrals in the general form so what will happen is if you do this is you get higher, you maybe get different powers of psi and psi in the denominator. So here a and b are integers, and p alpha is some polynomial in the alpha e's. Maybe it has coefficients in some Clifford algebra. But and the whole integrand is homogeneous, such that this is homogeneous of degree 0. So that's the general form of Feynman integral in parametric form. Of course, the P could be extremely complicated. Okay, so back to these scalar diagrams. The one-loop diagram can be expressed using a single function, well, or two functions rather. Well, the dilogarithm. The dilogarithm is defined by the following sum: x to the n of n squared. So this converges for mod x less than or equal to 1 and has an analytic continuation to c. It's a multi-valued function. And the logarithm. So any graph like this, you can always express the amplitude using just Li2 and log, where the x, it'll have a complicated expression in these with different arguments x, but where the x will be some function of the masses and momenta in some possibly quite complicated way. But in any case, there's a single function essentially that describes all one-loop amplitudes.
Which was the initial discovery of Feynman long ago.
That's true.
Feynman introduced the dilogarithm long ago for that purpose.
I'm skeptical. Well, we can discuss this. So the general two-loop diagram, two-loop amplitude is not known. So there isn't a function that you can look up in the canon of special functions. This also means that the singularities and the analytic behavior of the general two-loop amplitude is not understood.
But does it reduce to functions like of two variables or three variables?
So yeah. So here there's a theorem that if you take an arbitrary large number of external legs, you can always reduce to at most a certain number of legs. In two-loop, the corresponding result is not known. But I think it should follow immediately if one knew something from Hodge theory about weights. It should follow.
You need a function x is in general it's a rational function?
No.
No. It's
Algebraic function.
Algebraic?
Usually algebraic function.
yeah. So it typically involves square roots of a quadratic form in the masses and momenta. So even in a simple example like the triangle, it's in general it's a long formula. It's like I chose not to write it down. It's quite complicated. It's not something. So two-loop amplitude is not known in general. There's a special case that's become very fashionable at the moment, that's actually been studied for many years. So it's called the sunset, or for optimists, it's the sunrise diagram. So this is a particular two-loop diagram. So, of course, faced with these difficulties, what people typically do is make some assumption that certain masses are zero and so on and so forth. This has a long history, and it was recently solved for the general case with all non-zero masses and momenta. And the key names are Bloch, Van Hove, and Matt-Kerr, and Adams, Bogner, and Weinzierl. Sort of have very different approaches, but these have the sort of final word on the status of this integral. I recommend, if you want to know about the history, you can look at these papers. Sorry, I forgot to say something. The dilogarithm, the dialog is an iterated integral, so I can write it in a very simple integral form: 0 less than t1 less than t2 less than x. So let me take x between 0 and 1 for the sake of argument. Then it can be written as an integral just involving two differential forms. And so this is an example of an iterated integral on c minus 0 and 1. And for some bizarre reason, it's not fully understood, this space seems to, the functions on this space describes a vast number of Feynman amplitudes for reasons which are not completely clear. This, in fact, is an exception, but what it does involve are iterated, rather twice iterated elliptic integrals on some family of elliptic curves. And one way to write down, to get at the amplitude is by average, is this function, n in z. So here q has nothing to do with this q here. So q is, let me call it q naught. Q nothing is nothing to do with the q here. This is some function. It doesn't make sense. It's for many reasons. First of all, we're averaging a multi-valued function, and it's going to have singularities when n is either very big or very small, depending on this. So you have to regularize it in some way. But if you do that, you get some function, and this function essentially describes the amplitude here completely, where q naught here will be some function of the masses and q. So I won't say more about that. Next, there is so this is the first sort of difficult case. A huge class of amplitudes are known and are expressible using a finite class of functions called multiple polylogarithms, about which I think we'll hear a lot more this afternoon. So part of my job is to set up the afternoon speakers. So here's the definition of the multiple polylogarithm, some generalization of the dilogarithm. So it depends on r variables, and it is the sum 1 less than or equal to kr x1 to the k1 xr to the kr So that defines some analytic function on the region where the xi's, let's say, are strictly less than 1. And by analytic continuation, it extends to a multi-valued function on c to the r minus and then you have to take out the a certain class of diagonals given by the successive products. Sorry, this is actually C minus the origin to the R minus this class of diagonals. And this is nothing other than the moduli space of R minus 3 points on a sphere. So we think of this as R minus 3 particles on a sphere. Again, it's not entirely clear why a priori these functions should occur.
De XI à XJ, non?
Ah, yeah, thank you very much. Yep. So this is this is consecutive. This is just consecutive. Oh yeah, R plus 3, thank you. Absolutely. The other points are 0, 1, and infinity. Okay. So for some reason, this particular moduli space, of which in the case R equals 1, is just C minus 0, 1, it plays a special role, and it's not understood what the analog should be to describe all higher order Feynman integrals, if there indeed is such a thing. Okay, so something which is used a lot in physics, which I'll emphasize, but it is not valid in general at all. So I'm going to explain what it is and then say why one shouldn't extrapolate beyond its range of legitimacy, is that, first of all, they are iterated integrals. There's no reason to think that general Feynman integrals should be iterated integrals. And there's something very special, that they have a weight grading. So what that means is that the weight of, you can attach a weight to such a function. It's the sum of the indices. And a property of this weight is that if you differentiate the multiple polylogarithm of a certain weight, and there's an explicit formula for this, I'm just not going to write it out, then you can write this as a linear combination of functions of lower weight, again of multiple polylogarithms of strictly lower weight. In fact, weight 1 less. So there's some recursive structure in these functions, and this weight, if you keep differentiating in a certain way, you get to weight 0. And that reflects the fact that iterated integrals. But I really want to emphasize, because this is often in physics literature, it's said that this holds in general. It's not true. This is a very special property of this particular class of functions. Okay, next, so the sunrise was not of this type. It's something else. There should exist a class.
Est-ce que tu peux juste donner une idée du type de graphe pour lequel on a une telle expression?
I will leave that to the speakers this afternoon. I believe that that will be discussed in detail. So I'm just really setting up the afternoon talks. There should exist, so there is a well-defined class that we understand infinite families of graphs of this type. There should, beyond that, there should exist a class of multiple elliptic type, such that IG is multiple elliptic. So this is a sort of nascent theory. There are one or two papers defining what such functions are. This is not known, it's not been worked out at all. So that the first class beyond the polylogarithmic is completely unknown, save for one or two examples like this, maybe that and one other. And
Polyelliptic means hyperelliptic? No.
no, so it would mean something like this Li2, we sort of forced it to be elliptic on the Jacobi uniformization of the elliptic curve by averaging over Q. You can do the same thing for multiple polylogarithms. It's slightly more subtle, and that's a perfectly valid definition of a multiple elliptic polylogarithm. Alternatively, you could look at iterated integrals on the universal elliptic curve. That's a whole class of functions. It's in some sense the genus 1 analog of this story, and they should describe another large class of diagrams, and that class is not known. And so the boundary, again, the boundary where the polylog regime ends is not known. Something is known about it, but it's not known precisely. Okay, so now let me focus on some more specific examples. Which are of interest to number theorists. So I have half an hour, okay. So typically these examples are very difficult because there are lots of masses and momenta, and the amplitude is a function of many complex variables. And that's where a lot of the difficulty comes from. But often in practice you don't need such generality. And the things get easier if you make some restrictions on the momenta and the masses. So at the other extreme we have single scale processes. So these are where IGQM is a function of a single variable. So that could be, for example, all the masses are 0 and there's just one incoming momentum, or it could be where you just have one non-trivial mass. And what typically happens is that the dependence on that variable is completely trivial. And it will just factor out of the integral, out of the integrand. So what you're really saying is that the amplitudes are giving numbers instead of functions. So it factors out. And the coefficient is an interesting number. And then the question is, what can we say about the numbers that come out of quantum field theories? So here's one family of examples, which are in some sense the most exotic. So it's the analog of this sunrise. It's diametrically opposed to the polylogarithmic class where we feel we understand quite a lot. So these are the banana graphs, which have a lot of symmetry and are very interesting. And these were first studied by David Broadhurst. So let me do one example in complete detail. So we have the same picture like this. And what we're going to do is impose, first of all, let me set all the masses equal to the same mass, m.
But any number of masses, or just 3?
Just one here. So I'm going to put all masses equal, and I'm going to call it equal to m.
No, but are there M1, M2, M3, or M4, M5?
Ah, sorry, so the bananas, yeah, sorry, thank you. The bananas will be this family of graphs here. That's a banana. I don't know why it's called a banana. It looks nothing like a banana. Yeah. Yeah, sunrise banana. Yeah, I don't know. So the graph polynomial is this: alpha 1, alpha 2, plus alpha 1, alpha 3, plus alpha 2, alpha 3. The second graph polynomial, so these are all good exercises to revise the definitions of the graph polynomials I gave earlier. This is q squared alpha 1, alpha 2, alpha 3. And this polynomial xi gives this equation q squared alpha 1, alpha 2, alpha 3 plus m squared alpha 1 plus alpha 2 plus alpha 3 alpha 1 alpha 2 plus alpha 1 alpha 3 plus alpha 2 alpha 3, which is very nice and symmetric and defines a beautiful family of cubics. Okay, so in the next thing now, yes. So the next thing, so now Borja says, okay, now let work in D equals 2 dimensions, and put m squared. So this is not quite Euclidean space. I've been slightly dishonest here, but we'll put m squared equals q squared equals. So m squared equals minus q squared equals 1. And now, so now we set S, so using Broadhurst's notation, so you can look at his paper and directly compare with his conjectures. The integral is omega g. So if you look at the number of loops and number of edges, what happens is the psi drops out of the integral, and we get psi g. And so this m here in his notation is this graph where m minus 1 is the number of internal edges. So I don't know why he shifted the indices, but I'm going to stick with his indexing to make it more consistent. So if you do stick q squared equals minus m squared, of course the m squared just factors out of the integral, so we can just set m squared equals to 1. That's the coefficient. Yeah, m is not m. Thank you. Yes, that's unfortunate. Yeah, of course, the m counting the number of edges is not the same. But m is 1, so that's okay. So S bar 4 is what we've just computed. It's this integral. It's omega 3. It's this projective integral, alpha 1 plus alpha 3, alpha 2 plus alpha 3, very beautiful integral. And to work it out, it's a projective integral. So to work it out, we just work on some affine chart. So let's put alpha 3 equal to 1. And it's just d alpha 1, d alpha 2, alpha 1 plus alpha 2, 1 plus alpha 1, 1 plus alpha 2. So that's a very nice, completely convergent little integral there. And here's a list of what's known about these integrals. S bar 3 is 2 pi over 3 square root 3. S bar 4, which is this one, is pi squared over 4. S bar 5 is conjecturally, I'm not sure if this has been proved actually since I looked this up, but it should be 4 pi square root of 15 times the L function of a modular form. So this is some Dirichlet series that's beloved to number theorists. S bar 6 is experimentally given by 48 Riemann zeta of 2 times special value of the L function of a modular form, where F4 is a weight 4 modular form. It's an explicit product of Dedekind eta values. So this is something, I won't dwell on this too long, but it's something that number theorists care very much about. And it's not at all understood how and if at all this pattern should continue. Okay, and in general it's not known. After this, there's no conjecture for what these integrals should be. So you see that some very simple family of diagrams is producing some numbers relating to many active topics in number theory, and we really do not understand how to make sense of this. Okay, so that's in some sense the worst possible family of examples. Now let me turn to a completely different family of single scale examples. So these will be residues in massless phi to the 4 theory. And these are the examples that got a lot of us mathematicians interested. So now D is 4 again, and all masses will be 0. So I'll say that a graph is in phi to the 4. It turns out to be equivalent to the fact that all the vertices of the graph are of degree 4. So here's an example. So what we have in this situation is that the number of edges is twice the loop number. So the superficial degree of divergence is 0, and we're in the divergent case. So this quantity we had earlier has a pole here, and we're in trouble. But what we're doing is we're looking at the coefficient of 1 over epsilon in the Feynman integral in dim reg. And it turns out that this does not depend on the external momenta. It's just a number.
So it's a residue.
Yeah, so that's exactly what I was going to say. It's the residue. It's called the residue. And by total abuse of notation, I'm going to call it I again, because I'm running out of letters. So I'll just call it I. It's not the actual Feynman integral, it's the residue. And it's just given by the integral of omega g over psi g squared. So in the previous case, the integrals were special in that the psi dropped out of the integrand. These are special because the psi drops out of the integrand. Okay, so these integrals don't always converge. So a criterion due to Weinberg is that this integral converges if and only if G is what is called primitive. He didn't certainly use that language, but primitive refers to some Hopf algebra structure that came much later. But the condition is that for all strict subgraphs of G, the superficial degree of divergence of the subgraph should be negative, and that means that the loops should be bigger than twice. Sorry, the number of edges should be at least twice the number of loops. So the first example we saw already. So I leave you to work it out from the definitions that this is alpha 1 G alpha 1 over the graph polynomial squared.
So this graph should have always four external edges, I suppose.
Yeah, it does.
No, in general, therefore, do you agree? Because it's kind of renormalization.
Yeah. It'll always have four external edges. Absolutely, it'll always have four external edges. That's a consequence of this and this. By Euler's formula. Absolutely. So to work this out, we work on an affine chart. Let's say alpha 1 equals 1. So that's alpha 2 goes from 0 to infinity. D alpha 2 over 1 plus alpha 2 squared, and that is the number 1. So the residue of this graph is just 1. That's easy enough. And after that, they get a lot more difficult, as we'll probably hear more about this afternoon. So let me just give the first few examples, some of the first few examples. So the next graph which satisfies all these conditions is this graph. So here the residue is 6 times zeta of 3. This gives 20 zeta of 5. This here gives, oops, no, that's not good. This gives 36 zeta of 3 squared, which is the square of this amplitude. So there's some identity lurking, well, several identities lurking behind the scenes. And finally, this graph with 6 loops, which took many years to first compute numerically, which was done by Broadhurst and Kreimer. This with its external legs here, but it can now be done symbolically, because this is now known exactly, and it is 27 over 5 zeta 5, comma 3 plus 45 over 4. Okay, so what are these numbers here? So the zeta and r are the values at 1 of the multiple polylogarithms, and they're given by a nested sum. So this converges when nr is greater than or equal to 2, and these are called multiple zeta values. Okay, so this graph, this 6 zeta 3 turns up in many different quantum field theories. Essentially for the reason that was on this board before, that you can always write a general amplitude by putting numerators in, and the sort of numbers, you only get a finite family of numbers coming out. And it's this same zeta 3 that shows up in quantum chromodynamics and n equals 4 super Young-Mills. It shows up again and again. So there's nothing particularly specific. This theory seems very specific, but actually it gives a good indication of the quantities that are describing more general quantum field, or different quantum field theories. Actually. Okay, so multiple zeta values have a kind of weight. Have a weight, but now it's what I'm saying is totally abusive. You want to assign a weight to a number. You can't do that. It doesn't necessarily make any sense. And in fact, we don't know whether assigning this integer to these real numbers, MZVs, makes any sense at all. But conjecturally, these multiple zeta values are graded by the weight. That means that there are no algebraic relations with rational coefficients between them, between multiple zeta values of different weights. Okay, so I'll come back to that later.
You should say that the weight is half of the weight for geometry.
Yeah, I'll say that later as well, yeah. But so this is how physicists understand the notion of weight, and it's used a lot in modern, as a sort of guide to various things in the physics literature. So it is known that there is an infinite class of graphs, of such graphs in phi4 primitive, such that Ig, the residue, is a multiple zeta value, or a linear combination of multiple zeta values. So there's a criterion, so there's a combinatorial criterion. Okay, I won't say much about that. There are, at 8 loops, there are so-called modular graphs, whose amplitudes, whose residues we do not expect to be of this type. So somehow these numbers describe a vast class of these amplitudes, and something goes badly wrong at 8 loops. We get some graphs whose residues are expected to be something else. I don't know what to call them, but for want of a better name, they should be multiple modular values, certain types of numbers relating to modular forms. They're absolutely not of this class. Another comment worth making is that not every multiple zeta value seems to occur. So that means if you take the vector space generated by the residues of these graphs, they don't seem to fill the space of multiple zeta values. There's some very specific subspace with some very interesting properties. And finally, there's only one family of graphs for which we actually know the amplitudes. And these are the zigzag graphs. So you take a bunch of triangles like this, and you connect them from head to toe. And so zigzag 5 in this case, the index counts the number of loops. So a theorem I proved with Oliver Schnetz, which was a conjecture by Broadhurst and Kreimer for a long time, gives a formula for this amplitude. So let me write it down, because I think there's some interesting corollaries. So it depends on the parity of n. So this family of graphs gives every odd value of the Riemann zeta function. So we know in particular that all the odd zeta values definitely occur as amplitudes. In fact, from this you can deduce that the products of odd zeta values occur. But unfortunately, there is no other family of graphs whose amplitudes are known to all orders in this theory. And there is no family whose amplitude is even conjectured. So not much is known.
And here you mean it's a vacuum diagram, it's not a residue.
Yeah, this is residue here. So from now on, I always means residue. So in this section, so I've been a bit sloppy here. In this section, when I'm talking about residues, I'm calling the residue I, which is an unfortunate abuse of notation. But it has no Q and M in there, so I suppose it's... D equals 4, yes. D equals 4 in this here.
We can no more in 5 to 4.
I'm being sloppy, and they don't play any role because of this comment here. The coefficient of 1 over epsilon does not depend on the external momenta, so I can just ignore it.
These graphs with 4 legs, external legs, can be understood as closed graphs with degree 4 which remove one vertex. And probably 6 does depend on which.
So there are two things you can do. You can do what you just said, or you can also look at two-loop functions like this in 5-4 theory. So here you put 0 coming in here, for example, and you have just a single momentum coming in. And the amplitude of this is some trivial dependence on Q times the integral where you close up the external legs of a vacuum diagram. So these families of integrals are actually computing. If you take any integral like this and graph and you break a leg, it's computing the amplitude of a graph like this. And it's also computing the residue of the corresponding 4-point function. So these graphs are encoding lots of integrals at the same time. So here's a conjecture that that's an interesting challenge for a young person. It's in my paper with Schnetz. And so let G be a primitive graph of the type we're looking at in phi to the 4. So of course it satisfies ng equals 2hg in this section with hg loops. Then we conjecture, in fact, that the amplitude is strictly less than the zigzag graph. So the zigzag is somehow is the biggest possible Feynman amplitude in the theory. It's somehow reminiscent of volumes in hyperbolic geometry where you measure some complexity. These are pure numbers. So this is a positive number. So we conjecture that this graph is the biggest, and if this were true, it would imply a bound. It would imply that I of G over 4 to the H is at most asymptotically, by applying Stirling's formula to this, 2 over root 4 pi Hg to minus 3 over 2. So we give you some bound on the size of Feynman amplitudes. And of course, this is the first step in trying to understand whether you have the convergence properties or the resummability properties of your divergent series. And I think this conjecture is far stronger than what can be proved at the moment. Of course, you need to understand all the divergent graphs and the renormalization. But I thought that's a curious feature of this theory. And one is tempted to try to show that doing elementary operations on the graphs somehow always increases the amplitude or something. I think there may be something to explore there.
So, sorry, but why would this bound be important then if...
Well, if you want to understand, if you have the sum of all graphs, you have some divergent series, you need to know very precisely how many graphs there are and how fast they're growing.
I meant that usually this is removed by some renormalization, right?
So these residues are contributions to the beta function which are independent of all renormalization schemes. So these numbers, no matter how you renormalize, they will always be in there. Of course, there will be other graphs which have subdivergences that need to be renormalized. And there I do not know of a good, I mean, there are choices, so, but I don't know of an analog of this sort of theorem. But this, if you guess that all graphs of this nature, it would tell you something about the radius of convergence in the parallel plane. Okay, so some final remarks in the last 5 minutes. Should be rather open-ended. So I want to talk about this notion of weight that's been creeping in. That's been creeping into the picture. So the majority of the known amplitudes which were, so for example, the polylogs and the MZVs, which forms the bulk of what we know about at the moment, they had a grading, a notion of weight. So this grading is highly conjectural in the case of multiple zeta values. And we can ask where on earth this weight comes from and if it's got anything to do with physics. So recall that V, a vector space over Q is graded if and only if it admits the action of a group where, so lambda in Q star, lambda acting on V is lambda to the n V if and only if V of degree n. So we can think of this grading as a group action, and this suggests, amongst other things as well, suggests the possible action of a group on amplitudes, which a priori doesn't make much sense. So here's an important comment. In general, there should be a weight as well, but the weight cannot be a grading. If there is a notion of weight on all amplitudes, it certainly can't be a grading. So we should be careful of this. And it will be a filtration. It will be an increasing filtration. And if we stick with this, the normalization of the weights we've used up to now, which is the physicist's one, then we must expect half integer weights. So this is a fact that's well known to algebraic geometers, but I don't think it's been fully assimilated into the physics community. So what in mathematics we tend to do is multiply all the weights by 2, as Cartier pointed out earlier. So what is a conjecture then? So conjecturally, this is highly conjectural. There should exist a very large algebraic group of matrices. I should really say pro-algebraic. So it's like a group of infinite matrices, C, which acts on the space of generalized amplitudes which is the space which certainly contains, let's call it F of Feynman or something. So this is the vector space over which field I won't say, of regularized, because these integrals are possibly divergent, regularized integrals of the form of the general shape some numerator where a and b are integers and p a polynomial, which is homogeneous such that the whole integrand is homogeneous of degree 0. So in some sense this is like a vector space of all possible amplitudes you'd ever want to consider in any quantum field theory. Yeah, thank you. Yes, absolutely. That's a very good point. Let me fix fix d even. I think there should be something similar in odd dimensions as well. So this is the space of all amplitudes, and there should be a weight filtration, not a grading. So this is the space of amplitudes of weight at most something. So C acts on F, and the action of C should preserved by the action of this group. So there should be a huge group of symmetries acting on all possible amplitudes. So C would be called a cosmic Galois group.
You can include any other integrals on Schweik geometry. What's special about these guys?
There's a very, very small subclass of integrals.
Okay.
And what was surprising...
For any collection of integrals you can introduce.
Absolutely, you can certainly do that.
It's not, in conjecture. It's kind of, it's not conjecture, whatever, ignoring motives.
Yeah, no, but if you have to replace, not actual numbers, it's a transcendence.
Yeah.
Sure. Sure, this is... I agree, you can do this. The point, which I won't have time to mention, but the point is that amplitudes such as these you're finding are closed under the group. It's totally extraordinary. Yeah, absolutely extraordinary. There's no reason why the Galois conjugates of some crazy number like this should still be an amplitude. This seems to be the case. So in some sense, it is somehow the periods of some operad in the category of motives. It's a very strong condition. It's like the motivic fundamental group are the periods of a group in the category of motives. So it has some very, very strong, so they're very special formulae for the action. And here there's some sort of operad structure that's motivic. And so this is a useful concept. It really tells you something about amplitude. So it says that the action of this group on an amplitude will be expressible in terms of smaller amplitudes in some controllable way.
I mean, it's got product or whatever.
Yeah. So it's as I've said it's an empty statement if set up appropriately, but it will be a very powerful tool to study precisely this recursive structure. So this notion of cosmic Galois group is due to Pierre Cartier. And really, I say this because there were, in the abstract of one of the talks, there was mentions of a coproduct. So let me explain where this comes from. So we should have this group acting on the space of Feynman integrals of weight n. So one theorem, for example, is that this space is finite dimensional. So this is an extraordinarily strong fact. You have infinitely many graphs, infinitely many possible integrands, but this vector space is finite dimensional. That's some magical feature of these integrals. If you pick a random family, that's just not true. So quickly, the dual of an action is a coaction. So if OC is the ring of functions, and I'll finish here on this group, then the group law is equivalent to a coproduct on the functions So I think this may come up again this afternoon. And this action here, star, is equivalent to a co-action. F goes to F tensor OC. And the game is to compute this coaction on graphs and to use that to get information about amplitudes. And so that's one way, in this challenge I mentioned at the beginning, of how do we think about all amplitudes and how do we put some structure in all this information. One way to do that is to use this action of a group or a coaction, as I think we'll hear more about this afternoon. So I've overrun slightly, so I'll stop exactly there.
Any question? I don't have lots of questions.
Do you have an example of Galois action on a special class of this type?
Yeah, so this doesn't make sense on numbers because you run into transcendence conjectures. We don't know that zeta 5 could be rational, so we don't know that it makes sense. But indeed, in these in this family, the conjecture due to Panzer and Schnetz is that this space is closed under the space of under this Galois action. So so the group will send this amplitude to a linear combination of this and this. So it will map it. So this will generate a representation of the group, which involves zeta 5 and zeta 3, which are two smaller diagrams. So the fact that you're allowed to have zeta 5, 3, you know that you're allowed to have zeta 5, 3 is allowed to appear at this place and only in this place because you have previously had a zeta 3 and a zeta 5 in the right places before. You're not allowed to have a zeta 3 times zeta 2 because that would give a zeta 2 and there's no graph giving zeta 2. So it somehow rigidifies. You can see on these examples exactly how the group is acting. All conjectural.
I have a question about the non-primitive graph.
Yes.
You said that when the graph is non-primitive, the residue, the integral giving the residue is infinite, or the diverges?
So you need to, it diverges, and you have to renormalize it. So I didn't have time to explain.
Renormalize the dimension?
No, so we did an overall regularization for the overall divergence because the superficial degree of divergence was 0. So that's a regularization. But all the subgraphs which have superficial degree of divergence 0 need to be regularized in some sense as well. And that needs to be done consistently. So that's renormalization. So there's a way to do that. I didn't have time to explain that, unfortunately.
No more questions? All right, so let's thank Francis again.